Welcome to our last unit here, Unit 9.
That's so exciting.
We are going to start by talking about something called entropy. I had kind of touched on this a little bit back when we talked about something called enthalpy, which the two terms are very closely pronounced, you know, like one another. So you got to be kind of careful about which one you're talking about. So enthalpy, when we talked about that, we talked about heat. When we talk about entropy, we're talking about something different. Okay? So entropy, we also touched on it a little bit when we were talking back in Unit 7. I talked to you back then about entropy, and we gave it a letter S. And you can describe entropy in different ways. One way, the very common way, the very kind of simplistic way, is to describe it as the level of disorder. Okay? That's one way. In truth, it's a little more than that. Okay? So entropy is the measure of the thermal energy of a system divided by a unit of temperature in Kelvin. This energy is unavailable to do useful work. Okay? So essentially, one of the other ways that you can think of it is entropy can be thought of as a measure of the energy lost to molecular disorder or randomness. So you know how when you are trying to find something in your room and your room is a total pigsty and you're just like, I can't find it?
Yes.
Okay.
That's how I feel right now.
That's what it's like when you have like increased temperature. Increased energy is you're going to lose a lot of your energy trying to find stuff in that disorder. If you had it all nice and neat and, you know, organized, you'd be able to go in and grab the thing and walk right out. Okay? But you end up losing a lot of your energy to that disorganization. Entropy's units are joules per Kelvin, and this is important. These are measured in joules per Kelvin. And why that becomes important is when we were doing enthalpy, it was measured in kilojoules. Okay? So that means when we try to merge these two together in a couple different equations, when we have to do calculations with both enthalpy and entropy in the same equation, you have to convert this guy over to kilojoules. So you're going to have to take whatever he's measured in and divide by 1,000 to get that into kilojoules. Because there's 1,000 joules in a kilojoule. Does that make sense? And I'm going to start harping on that from day one of the unit, and I'm going to keep kind of reminding you of it over and over again until we get to the exam May 2nd. All right, positive values indicate that the system increased in entropy. So it became more disordered, or it had more, they call it microstates. Okay, more places for that energy to be used up at. Negative values then say that the entropy decreased. So your entropy when you clean your room will end up decreasing. So the third law of thermodynamics states that the entropy of a perfect crystal at 0 Kelvin is 0. Okay, but you're never going to get to 0 Kelvin because that's absolute 0, and we don't get to that point. So here, we consider two particles in this container. The container has two different sections. There's one way to have both particles on the left. There's one way to have them both on the right. And then there's two ways to have the particles on each side. It is more probable to have one particle on each side, which means that if we have a system with two particles in two sections, it's more likely that at any given time, the particles are going to be spread out. An actual chemical system, like a beaker or a balloon, contains a large number of these possible sections. In science, we call these invisible sections microstates. Okay, so if we had a balloon here, okay, could all of the molecules in there be bunched up right here?
No.
In theory, yeah, they could. Okay, but what is the but here, I'm going to save you. But what is the likelihood of that happening?
Like 0.
Very, very slim. Okay,
Got 0. That's
so what we tend to see is that they are going to spread out and be spread out as far apart from each other as possible. They're not going to be all bunched up. In theory, could it happen? Yeah. In theory, could I flip a quarter and it turn heads 100 times out of the 100 times I flipped it?
It's possible.
It's possible, but in reality, it's not very probable. Okay?
Oh
If we had Humpty Dumpty sitting on a ledge and Humpty Dumpty fell off that ledge, they say that all the king's horses and all the king's men couldn't put him back together again. Is it possible for us to sit there and put all of those eggshell fragments back together? In theory.
You would need a microscope.
In reality, is it really going to happen?
Probably not.
No. So when we call those possibilities, you know, when that egg falls off and it breaks up into 500 pieces instead of 499, when we put all of those possibilities together, those are called microstates. Okay? So when particles or energy in a system are more spread out into the microstates, we say that the system has more disorder or entropy. So for example, here we have our solid, and I'm going to move this so that we can have solid, liquid, and gas. This solid has fewer microstates, fewer possibilities for how those atoms are going to be arranged because they're locked into that crystal. Okay? The liquid has more possible ways that it could be arranged, right? Because they can flow past each other. This molecule could be here, or it could be here, or it could be here, because they're able to flow. Does that make sense?
So the
Are you on your phone? You bring that thing up and put it on my desk right now.
I'm embarrassed.
Allie forgot her phone at home.
Yeah, I'm not a phone cleanse. I did it by choice. You need it.
Solid.
It's like a puzzle.
About what?
Like all the pieces fit.
And I don't know where to go. Where to go?
How about church? Church.
Can I commence?
You didn't bring me to my church.
Not right now. I want to talk about microstates right now.
I'm kidding with you. Proceed.
The solid, those particles are locked into the place. So the likelihood of this molecule being there in that same spot in an hour is pretty darn good. Okay? So the disorder in a solid is much less than it would be in a liquid where they're able to flow past each other. Okay? In a liquid where they're able to flow past each other, they're able to be rearranged differently. But in a gas, they're able to be arranged even more because there's even more places for that to be able. It's not just going to be down at the bottom where the liquid sits. It can be anywhere in that container. Does that make sense? So the entropy, this has the greatest entropy. This is in the middle, and then this would have the least. Okay? If you place the same amount of gas in two containers with two different volumes at the same temperature, the gas in the container with the larger volume will have a greater entropy. So if I have a container this big, I have fewer possibilities for that gas to be in different locations versus a container that's this big. This has more options to be here, 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 here. Do you follow me? Okay, so that's what they're saying here. When you look at an equation, there is an increase or decrease in entropy by comparing the moles of gas on each side of the equation. If the products have more moles of gas, then there's more entropy, and the delta S will be positive. Entropy also increases when energy is more dispersed within a system. So we can compare two systems at identical temperatures based on the kinetic molecular theory. The system with a higher temperature will have particles that have a greater kinetic energy. Thus, the energy distribution on the particles will be greater, and that leads to a greater entropy as the temperature of the system increases. So here, we're going from 1 mole of gas to 2 moles of gas. So the entropy is increasing. If we have an increase in temperature, you're also going to have entropy increasing. If you take something that was in a solid form and you dissolve it, then in a liquid or in a gas, it has a more of a chance of being randomly placed. Does that make sense? It's not going to be locked in that matrix. So its entropy would increase. As we go through phase changes, endothermic phase changes, entropy will increase. A reaction which results in an increase in the number of moles of gas will increase entropy. And then gases expanding will also do that. And then just the opposite for all of these will cause the entropy to decrease. Okay, so for example here, we have water, and then we've taken that and we've changed it, okay, into hydrogen and oxygen. We've gone from 2 moles of gas here to 3 moles of gas here. Here, we've taken a solid as a solute, and we've dissolved it in a solution. So you can see here that that solute is more randomly placed now compared to where it was there. So entropy is increased. You too. Stop. All right. For each of the following pairs, choose the substance with a higher entropy and explain why. So here we have a gas and a solid. Which one is going to have the higher entropy?
Gas.
Yeah.
The gas will have the higher entropy, okay? And the reason why is because as we disperse that gas, that has more microstates. It has more places that that gas can be, okay? That makes sense? All right, what about the next one? We've got helium gas at 2 atmospheres and helium gas at 0.02 atmospheres.
0.02.
The pressure is decreased.
0.02.
Okay, why?
Because it can go, it isn't as pressed together.
Right,
It can
yep.
go wherever it wants.
At lower pressures, the gas is going to expand. Okay, so gas will expand at these lower pressures, and it's going to be more randomly placed in that space then. All right, here we have CaCO3 solid, CaO plus CO2. So you've got,
CaO plus CO2.
right. So you've gone from 1 mole to 2, and you've gone from a solid to some of it going into a gas. So there's 2 reasons here that would cause this entropy to change. Does that make sense? All right, we do. Formation of ammonia gas is exothermic. That is a spontaneous. That means that it happens without any outside intervention, adding in energy or anything like that. And that happens at low temperatures. So they want us to complete this reaction over here. And this is something that a lot of you need to start being very careful of. You need to count how many things you have over here and make sure that you have the same amount of things over here just rearranged. Okay? So over here, I've got 2, 4, 6, 8, 10, 12, 14 of these. And oftentimes, I will even write down off to the side how many of these I've got. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. See how I got that? How many of these blue blobs do I have? 6. Okay. I need to make sure that when I get done over here, I haven't added any extra ones and I haven't lost any. And where does that go back to? What law?
Third law.
Yeah. Conservation of mass. Okay. I'm making NH3. So I'm going to make, I have this, and I need to have 3 hydrogens for each. So if I divide this, 14 divided by 3 is what?
Not 12.
14.
4 point something.
Okay. So that means that I'm going to be able to make 4 of these. So I'm going to start out with that. Okay. So that's my solid blue. I know I'm not doing a stellar job of coloring those in, but just for time's sake. Okay. And then I've got my hydrogens, and I'm going to go 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3. All right. How many hydrogens do I have left over then? 2. So I need to draw a hydrogen molecule here. So I've got all 14 of my hydrogens placed. And what am I missing?
2 nitrogens.
2 nitrogens. And remember, they're going to stay together. They're diatomic. Okay? Go back and make sure that you have the same number of stuff here that you had over here. Now, I've gone from 4 moles here to 2 moles here. What has happened to my entropy?
It has decreased.
It has decreased, okay? And it has decreased because we've gone from 4 moles of substance down to 2 moles of substance. Questions about that part of entropy before we move on to some calculations with it? All right. So absolute entropy and entropy change is the next one. All right. And this should look similar to you because we've talked about when we had our equations before, we had H's here. Do you remember doing this with H's? We had products minus reactants. You had to do the delta of each of them. Okay. Now, entropy can be described both qualitatively, that's what we did in 9.1, and quantitatively. That's what we're going to start doing here in 9.2. In definition, entropy is the measure of disorder. It's really the measure of microstates in a system. In 9.1, we described it again qualitatively. We were kind of able to determine if it was going to increase or decrease. Now we're going to start using numbers. The second law of thermodynamics states that the entropy of the universe increases for spontaneous, or we don't like this term so much. Spontaneous in your world reminds you of what idea? When you say that something happens spontaneously, what does that mean to you?
Just random, out of the blue.
Okay.
No.
What about fast? Okay. Everybody thinks that it's fast. Okay. And it's not necessarily fast in chemistry. Okay. Our definition of it here, spontaneous means that I don't need to add any kind of external intervention. I don't need to plug in electricity to make it happen.
It just happens.
It just happens. But it may not just happen boom like that, like super fast,
It
like
takes
lightning.
time.
Okay? Sometimes. Okay? Spontaneous here, we like to get rid of the word spontaneous and we like to add in thermodynamically favorable. Okay, so thermodynamically, and there's an O in here, thermodynamically favorable is what we like to put in. Because like rust on my truck, okay?
That's spontaneous.
It is a spontaneous reaction.
It took forever.
But it's taken, 10, 12 years to get that rust to form, which is good. But it's a spontaneous reaction. It's just going to happen on its own. Okay? I didn't have to plug in electricity to make it happen. I didn't have to do anything special. It just over time, starts to happen. So you need to start in your mind getting rid of the word spontaneous and replacing it with thermodynamically favorable. So if we have this where our system plus our surroundings, if that is greater than 0, then it's going to be a thermodynamically favorable reaction. If it's equal to 0, then it's at equilibrium, and if it's less than 0, then it will not be thermodynamically favorable. All right, let's focus on the entropy of the system then. Reaction, which we're studying, we can calculate the energy of the system, which is the same as the change in the entropy for the reaction, by adding together the standard entropies for the products multiplied by their coefficients. And you guys have done something similar to this. And I gave you back in Unit 6, I believe it was, I gave you a table of these. There was like an appendix that had a bunch of these, like 5 or 6 pages. Do you remember that? Okay. And I said, don't lose this. We're going to be coming back to it in Unit 9. Okay. So the delta S for our reaction is going to be the sum of the delta S for the products minus the delta S for the reactants. The values then can be found in the back of your textbook. I know you don't use that often, so if you go and you look in your Unit 6 stuff, you should be able to find that file again. Okay? So if the reaction is this is what that would look like, except these need to be raised up to the coefficients here. Okay? Or no, it's just multiplied by, I'm sorry, they're multiplied by that. Okay? So we need to use our data over here. And this is typically what they'll do on the AP exam, is they'll give you a chart like this with several different items in it. And you just have to figure out how to manipulate those. So you would never have to memorize these delta S values. Okay? So we are going to start here with our products. We're going to take our NO2, which is here. I've got my 240.1. I need to multiply that by 4 because of the coefficient here. I need to take my water, which is 188.8, and I need to multiply it by 6. And I'm going to get a value for that. And then I'm going to subtract whatever that is from my reactants, which are here. So NH3 is 192.8 times 4. And oxygen, so I would add these. I'm going to add these together. Oxygen is going to be 2052. And I need to multiply that by 7. And then I add all of those together. Okay, so multiply these out. This is going to be 960.4. This is going to be 1132.8. And if I add those values together, I get 2093.2. This one is 771.2. And this ends up being 1436.2. So this is 2207.6.
Negative.
So now I'm going to take this value and I'm going to subtract this one. And that's going to be a negative 114.4. And what are my units?
Kilojoules per mole. Joules per mole. Times Kelvin.
Yeah. Joules over moles times per hour.
It's joules per mole Kelvin. I got that from right here.
You're just mad because I'm the best beatboxer, right?
Is someone trying to learn? She said, shut the fuck up.
Hey, watch that language,
Yeah,
please.
I can't believe you didn't even say that.
That is so funny.
No, I know Entropy is
All right, so let's look at the next one here. Using the data here, we're going to calculate our delta S for this. We have our A2B2. So that is, well, I'm going to start with I always start with my products, actually, so that they're over here, and then I subtract that from my reactants over here. Does that make sense?
Sounds glorious.
Okay, so I'm going to start with my C2. So that's going to be 191.6 times 1 is 191.6. I have my A2B. That's right here. That's 188.1. I'm going to multiply that by 4. And that ends up being 752.4. Add those two values together, I get 944. Then I'm going to come over and do my reactant side here. So my reactant side is going to be 109.6 times 2. So that ends up being 219.2. My C2A4 is 121.1 times 1. And I add those two values together, and I get 340.3. Subtract these two values from one another, and my answer ends up being 603.7, and that's going to be joules per mole Kelvin. Questions? All right, you have 9-1 and 9-2 that will be due on the 11th then, which is tomorrow.
And you treat your dog.